Welcome friend. Welcome to Math A to Z. Our topic of this class is an important theorem called Bolzano-Weierstrass Theorem, and we discuss this theorem in 2 points of view. The first point of view, that is in the point of view of sequence, that is the sequence of real number point of view, and the second point of view is the set of real number, that is the Bolzano-Weierstrass theorem in sequence of real number and Bolzano-Weierstrass theorem in set of real number. Now we state the Bolzano-Weierstrass theorem in 2 points of view, and then we proceed to the proof and its example. The statement of Bolzano-Weierstrass theorem in sequence of real number is: every bounded sequence has convergent subsequence. Here two words important: bounded sequence, then convergent subsequence. And Bolzano-Weierstrass theorem in second point of view, that is set of real number, we state that every bounded infinite set, bounded and infinite, every bounded infinite set has at least one limit point. Okay, now we go to the proof of Bolzano-Weierstrass theorem in sequence of real number point of view. Before going to the proof of this theorem, we state another theorem which is called nested interval theorem. Now, statement of the nested interval theorem. Let IN, capital IN, be a sequence of closed interval such that IN plus 1 subset I for all n belongs to capital. For all n belongs to capital. That is, the sequence IN is nested sequence of closed interval. What is nested sequence? Nested sequence of closed interval. Now we discuss in short which is nested sequence of closed interval. Here I1 closed interval A1, B1, I2 closed interval A2, B2, IN closed interval AN, B, IN plus 1 closed interval AN plus 1, B. Here, if I1, this closed interval like that, A1 and I2, this closed interval is like that, and so on AN, BN and A plus 1, A plus 1, and this is like a nest. So this type of closed interval or this type of sequence of closed interval IN is called nested sequence of closed interval. And in the second partition, the length dn, which is length IN equal to AN dn. So the length dn of IN equal to mod dn minus n. The length dn minus n, this is the length of the interval. This is the length dn. So dn of IN tends to 0. This is tends to 0 as n tends to 15. N tends to 15. Then nested interval theorem state that conclude that there exists exactly one point, which is common to all the intervals, which is common to all the one point, exactly one point, which is common to I1, I2, I3, and so on. This is the nested interval. Now we go to the proof of Bolzano-Weierstrass theorem. Here, sequence is bounded. So we let xn, the sequence is bounded. From the definition of boundedness, there exists a real number capital M greater than 0 such that mod xn less than capital M for all n belongs to capital M. This is the set of natural number. This is the set of natural number. That is minus m less than xn less than m for all n belongs to capital M. So all the points of the sequence xn lies on the closed interval minus m to m. Okay, minus m to m. This is 0, this is minus m, and this is m. Now, for all n belongs to n, every member of xn, that is x1, x2, x3, and every member, all lies in minus m to m. We divide this interval into two equal intervals, which are minus m 0 and 0 m. Since in this interval infinite number of member of xn lie, so at least one of the intervals must contain infinitely many member of the sequence xn, be in xn, be in this interval or be in this interval or in both the intervals. For this theorem, we take any one of them in which infinite number of member of xn lies. Let in this interval or rename this interval, maybe this or maybe this, as I1. Rename this interval as I1. That is, I1 may be minus m to 0 or maybe 0 to m, in which infinite member of xn lie. Now, if this, so it can be divided into two intervals, or if this can be divided into two equal intervals. Now, the length of I1, that is d1, equal to n, either m minus 0 or 0 minus n. In both cases, this is n. Now, if this is I1, I1 can be divided into two equal intervals. And in similar argument, by applying similar argument, we say that at least one subinterval must contain infinitely many member of xn. Rename this interval in which infinitely many member of xn lie, rename as I2. So, it is clear that the length of I2, that is d2, equal to m by 2. And proceeding in this way, we get In such that dn equal to m by 2 to the power n minus 1. Here m by 2 to the power 2 minus 1, that is 2 to the power 1. Here m by 2 to the power n minus 1. Here we get a sequence of closed interval. In. In this picture, if we take 0 to m, this is I1. Same as minus m to 0, if we consider this is I1. This is I1. So, I2 is either this or this. If we take I2 is this part, then this is cancelled. Now, I3, half of them, I3 is, if we cancel this part, so I3 is only this interval. So, it is clear that I1, this is I1, this is I1, half of them, this is I2, half of them, this is I3. So we can write I1 is a superset of I2, a superset of I3, and so on, in plus 1. So this set of closed interval is nested sequence of closed interval, and together with this we have dn equal to capital M by 2 to the power n minus 1. This tends to 0 as n tends to infinity. So this is the first condition and this is the second condition. Both the conditions hold for nested interval theorem. Which theorem? Nested interval theorem state. Which is the statement? The statement is there exists exactly one point common to all the interval. So this is in I1, this is in I2, this is in I3, and this is in In also, and so on. Let this point be L, this point be L, which belongs, or all n belongs to L. Now we consider a member of Xn, that is Xn1. A member of Xn, that is Xn1, belongs to I1. A member of Xn, that is Xn2, belongs to I2, but satisfying the condition such that N2 greater than N1. Here N1 and N2 are both natural numbers. And in similar manner, we get a member Xnk belongs to Ik such that Nk greater than Nk minus 1. So we get X1, Xn1, Xn2, Xnk. Xn1 belongs to I1 and L also belongs to I1. Xn2 belongs to I2 and L also belongs to I2. And similarly, L also belongs to Ik from this condition. Now we get a subsequence Xnk of Xn, and Xnk and L, both the point belongs to I. This is Ik and here Xnk and L. So we must have mod of Xnk minus L less than, obviously less than, m by 2 to the power k minus 1, since the length of this interval Ik is m by 2 to the power k minus 1, and in this interval this is and this is a 2 point. So the difference of 2 point must be less than m by 2 to the power k minus 1. Now we get m by 2 to the power k minus 1 less than epsilon for any pre-assigned epsilon greater than 0. If 2 to the power k minus 1 greater than m by epsilon, if k minus 1 greater than log m by epsilon by log 2, that is if k greater than this plus 1. So if we choose a natural number m equal to box of log m by epsilon by log 2 plus 1 plus 1, then we can write, then we can write mod of m by 2 to the power k minus 1 minus 0 less than epsilon for all k greater equal to, for all k greater equal to n. K greater equal to n. That is, we can write mod of xnk minus l less than epsilon for all k greater equal to n. So we write limit k tends to infinity xnk equal to l. That is, we get a subsequence xnk of the sequence xn such that xnk is convergent and converts to l. And this is the proof of Bolzano-Weierstrass theorem. Now we go to the proof of Bolzano-Weierstrass theorem in second point of view, that is in the point of view of set of real number. Again we state every bounded infinite set has at least one link point. Here the set is bounded and infinite. Proof. Let S be the bounded and infinite subset of real number R. S be the bounded infinite subset of real number. Since it is bounded, so the S has infimum and supremum also. Let infimum of S equal to small m and supremum of S equal to capital M. So we can write small m less equal to small x less equal to capital M for all x belongs to S. This is the property of supremum and infimum. Now here we consider another set, capital H. This is a subset of real number, and the definition of H as x belongs to capital R such that x greater than infinitely many member of S, or it can be written like x exceed infinitely, and this is the same, infinitely many member of S, x greater than or x exceeds. Now here M obviously belongs to capital H. Since M is the greatest member for all x less equal to M, So M obviously exceeds infinitely many member of S. So M belongs to capital H, that is capital H not equal to 5. Now capital H not equal to 5 and let Y, small y, belongs to capital H, any element of capital H. So this element must also exceed infinitely many member of S. Since Y exceed infinitely many member of S, so we can write Y greater than M also. This is the infimum for all x less equal to greater equal to M. So Y greater than M. But no member of H less equal to M, because no member of H less equal to M cannot exceed the infinitely many member of S, since M is the infimum of S. So H is a non-empty subset. H is a non-empty subset of real number which is bounded below. Because for all y belongs to H imply M less than y, bounded below. Non-empty set of real number bounded below. So H must be an infimum. Let Xi be the infimum of H. Xi be the infimum of Xi equal to infimum of H. So from the definition of infimum, for any epsilon greater than 0, there exists at least one Z, such that Z less than Xi plus epsilon. This is the second property of infimum. Also, for every Z, one Z belongs to H. For every Z, it is Xi. That is equal to Xi, because Xi is the infimum of H and Z belongs to H. So we can say that Z belongs to H. And Z less than Xi plus epsilon. And greater than Xi minus epsilon also, because this is greater than Xi, greater equal to Xi. So Xi minus Z greater than Xi minus epsilon. Now Xi be this is the set H, and xi lies at that position. So xi minus epsilon lies outside the set. So xi minus epsilon cannot exceed infinitely many member of S. But xi plus epsilon in between H. So in this interval, or in this neighborhood, there must exist infinitely many member of H, because xi minus epsilon cannot exceed infinitely many member of S, and xi plus epsilon exceed infinitely many member of S. So in this interval or in this neighborhood, there exists infinitely many member of S, and since xi minus epsilon to xi plus epsilon contains infinitely many member of S, so xi must be a limit point of S. Xi must be a limit point of S. Now we touch the proof. We want to show at least one limit point of S, and this is the limit point, and this is the proof of Bolzano-Weierstrass theorem in set of real number points of V. Now we see the example of these two theorems. We know that -1 to the power n, this is a bounded sequence whose bounds are -1 and 1, and clearly this sequence have two subsequences, x 2n equal to -1 to the power 2n, that is equal to 1. This is constant sequence, that is tends to 1, and x 2n minus 1 equal to -1 to the power 2n minus 1, that is equal to -1 tends to -1. So this sequence have two convergent subsequence, and for this theorem we see that the set AB closed set, or also we can take open set or open interval of real number, and we know that this bounded infinite set have infinite number of real numbers. Here all the points are limit point. Also here all the points are limit point. Also A and B are the limit point. So the set bounded and infinite, so it has limit point. Now come to the last point. Here in both the theorem, bounded, this is not necessary for this. That is, if the set or if the sequence, if the set or if the sequence be unbounded, then the set or the sequence may have limit point or may have convergent subsequence. If we consider the set of rational number set, this is obviously unbounded set, rational number unbounded set, but it has infinite number of limit points. All the point of Q are the limit point of Q. So this is an unbounded set, but it has infinite number of limit points. Similarly, we get many examples of this theorem and this theorem to show the bounded is not the necessary, but the bounded is the sufficient. That is, if bounded, then convergent subsequence. If bounded, then at least one. Okay, thank you for